This piece of metal, 2 inches in diameter and 5/8 of an inch thick, is known as plutonium. It weighs only 2 pounds, yet within it is the energy of 2,000 tons of coal. Plutonium didn't exist on Earth until man brought it to life in a nuclear reactor. Yet today, this seemingly mysterious metal is the object of intensive research in many laboratories throughout the world. And tomorrow, plutonium will be furnishing much of the electric power for your home. In the next half hour, we'll see how scientists are developing this fuel of the future. Challenge is produced through a grant from the United States Atomic Energy Commission's Argonne National Laboratory. This is the Plutonium Fabrication Building at Argonne. Here, in one large room, are the elements of a complete metallurgical plant under glass. Foundries, rolling mills, presses, machine shops, and an assembly line. In this series of tightly sealed enclosures, many of them interconnected, scientists work with plutonium, shaping this material into test specimens and into actual fuel assemblies for a nuclear reactor. There's an important reason for these precautions. Plutonium, in addition to being man's most important potential source of energy, is one of the most toxic substances known. It's necessary that every speck of plutonium be kept safely contained, where it can do no harm. These enclosures allow the scientist and the technician to handle plutonium not with fear, but with respect.
They're about to place some plutonium in the glove box line now, Norman. The health physics man monitors the container, and the technician takes it out of the bird cage. That's what we call the crates we use for shipping plutonium. They're built so it's impossible to stack too much plutonium closely together. Stacking too much of it together could cause a nuclear reaction. This first glove box has an atmosphere of air. The plutonium itself is in an inner container, which is an ordinary tin can. Now they're passing it through the pouch into a helium-filled glove box. They take it out of the helium-filled pouch. This is necessary to keep air out of the helium system. Then they put it on the conveyor and take it to the glove box where the plutonium will be weighed. After opening the can, the man removes the plutonium to weigh it. Naturally, weighing is an important part of the process, since reactors require exact quantities of fuel in each element. Then, too, plutonium is very costly, and we're as accurate about its weight as we would be with gold or platinum. Even after we've established the amount of plutonium in the fuel charge, a second man must verify the weight. To the plutonium, we add carefully measured amounts of metals with which it will be alloyed. In this case, he will be adding small amounts of molybdenum, ruthenium, rhodium, palladium, zirconium, and niobium. These are exotic-sounding materials, but they are important constituents of the reactor fuel.
This was Arthur Shuck, a senior metallurgical engineer at Argonne, who was responsible for the basic design of this building and now directs the activities of those who work here. Art, what's the function of those exotic-sounding materials you mentioned?
They add stability to the fuel. They make it strong and better able to withstand high temperature and irradiation. But more important, they simulate the fission products of the nuclear reaction that are not easily removed in process. We are developing a fuel that can be reprocessed without removing those fission products. Finally, uranium is added. This dilutes the fuel and makes it less powerful. There is far more uranium than plutonium in the reactor. Inside the reactor, the uranium will be converted to plutonium. We call this process breeding when the reactor produces more plutonium than it consumes. The reactor is called a breeder reactor. We are very interested in the breeding process because breeder reactors will be required in the future if we are to use our total nuclear resources.
Before we go too far afield, let's talk to Dr. Frank Foote, director of the Metallurgy Division at Argonne, to learn something about the development of plutonium.
Okay, turned off. As you've just learned, Norm, we can convert atoms of uranium into plutonium. This was first done during World War II in atom smashers or cyclotrons. This produced enough material to enable us to determine its chemical and nuclear properties, but not its metallurgical properties. We did not obtain appreciable quantities of plutonium until it was made in nuclear reactors, much as is done today. During World War II, we needed plutonium for the atomic bomb program. And in order to acquire the required amounts, a large reactor complex was constructed at Hanford, Washington, just to make this material.
The first use for plutonium, then, was the atomic bomb.
Yes, this is true. It was a natural selection for weapons use because it is a much more concentrated form of energy than is ordinary uranium. However, here we're studying plutonium as a fuel in power reactors for the generation of electricity.
Once it's in the reactor, does plutonium act much the same way uranium does?
Essentially, it does. However, it presents many more complex problems than did uranium, and at first it appeared to be a metallurgist's nightmare.
A metallurgist's nightmare. Why do you say that?
Well, for example, if pure plutonium is heated from room temperature to its melting point, it undergoes rather severe distortion. This is because the pure metal exists in 6 solid forms at different temperatures. Each of these forms has different physical and mechanical properties. In addition, the material burns readily in air, and of course it is toxic. And in order to use it as fuel in a nuclear reactor, it must be sealed into an airtight jacket.
Now, that sounds very difficult. How do you do that?
The plutonium is mixed with other materials, and the mixture is then sealed into a capsule, which is strong, resists corrosion, and transmits heat generated within the plutonium. There are many problems to be considered, both from the standpoint of the fabrication and the reactor design. The major purpose of this particular building is to develop methods to carry out this fabrication and to produce specimens for testing the suitability of the fuel.
It's amazing how much we've learned, Norman, in the 20 years plutonium has existed. We know that pure plutonium cannot be used. It has very poor properties and just is too powerful as a reactor fuel. We know also that it forms compounds and alloys with many other elements, and some of these appear to make satisfactory fuels. We are beginning to understand why fuel elements fail. We believe that this should enable us to make reliable fuels for high-performance reactors in the future. In this laboratory, fuel manufacturing processes are being worked out, and fuel elements are being made. This is a test fuel rod. You'll notice that I can handle it without protection. That's because it's sealed in a jacket, which has been tested repeatedly for leakage and radioactive contamination.
How are the fuel rods used in the reactor, Art?
The fuel rods are assembled in bundles like this one. They're assembled with other materials in a hexagonal tube in about this position. This assembly is called a fuel element. The reactor core contains many thousands of the fuel rods in the fuel elements that are installed in it.
Thousands? Why can't you just use larger pieces of plutonium?
If we were to use larger pieces of plutonium, the fuel rods would get just too hot. We must provide for the continuous removal of a very large amount of heat. To do this, the reactor is immersed in a recirculating fluid. The reactor in which we will use these rods is immersed in sodium. This is a diagram of that reactor. The fuel section is about the size of a bushel basket. We've made up a display which shows the fuel rods in this reactor. The fuel is in a pin, which is about 1/8 of an inch in diameter by 14 inches long. It is enclosed in a niobium jacket.
Niobium, why do you use it?
Niobium will not combine with the fuel or with the sodium. A thin layer of sodium must be provided between the fuel pin and the jacket. About 10 kilowatts of heat is generated in each fuel pin. Without the sodium, the fuel would melt. We must also provide a space for the expansion of the fuel and the sodium and for the accumulation of the fission products.
Do all fuel rods look like this?
They all have sealed outer jackets, but the form of the fuel may be different for other reactors. Some reactors use pellets of oxide or plutonium carbide, and some have packed powders. Fuel elements in some reactors are made of flat plates. This building is equipped to make many types of fuel elements, and right now we're making rods of the type that we have just been looking at. They will be tested in the reactor whose core we have seen.
Let's talk about these enclosures for a moment. As we've said, they're designed to protect the people who work here against radioactive contamination.
The boxes actually have two purposes, Norman. They are protection against the alpha radioactive plutonium. They also prevent oxygen from reaching the plutonium. You'll remember we said earlier that plutonium and its alloys burn quite readily in air. Most of these boxes are helium-filled. Helium is chemically inert, and it will not support combustion.
I suppose that the gloves attached to the portholes in the boxes are thick enough so that they will protect the workers against the alpha particles.
Actually, a piece of paper would stop the alpha particles. Plutonium is dangerous only if it gets into your body. The tiniest bit could do a lot of damage if inhaled or swallowed, or if it entered your bloodstream through a cut. All the glove boxes are gas tight, but as an extra precaution, the pressure inside is less than that of the atmosphere. So any leakage is inward rather than outward.
What would happen if one of the windows were broken?
We have provided for that emergency too. If the pressure in the glove boxes suddenly increases, an automatic control opens a valve to an exhaust. At the same time, the helium system is isolated to keep air from the other glove box lines. That covers the ventilation system.
Do the red lines on the floor mean anything?
They are part of our nuclear safety control. The red lines divide the room into zones. We can handle and fabricate only limited amounts of plutonium in any zone.
How much fuel can you make at any one time?
Not a very large amount. An important limiting factor is nuclear criticality. You'll remember that a reactor becomes critical when it is loaded with plutonium and the control rods are withdrawn.
In other words, the chain reaction starts.
Exactly. Spontaneous criticality is something that we must guard against at all times when we are handling, storing, or fabricating plutonium.
You mean if you have too much together at any one time, a nuclear reaction will begin automatically?
Yes?
I believe you said that's why you ship plutonium in the birdcage containers, to keep it apart.
Right, but there are other factors. The shape of the piece is important, and where it is located in the reacting system. Also, the sizes of the pieces have a great deal to do, and whether they're flooded with water. A very much smaller amount of plutonium is critical underwater than when dry, and special precautions are taken to prevent flooding. Generally, we do not work with more plutonium in any glove box or zone than about 1/2 the amount which we could handle safely under the worst possible conditions.
How much is that?
The exact amount will vary with the dilution or the process. Generally, we can work with 2.5 kilograms or about 5.5 pounds of solid dry plutonium. Since plutonium is about 3 times as dense as steel, that is a piece about this size. If the process is carried out underwater, that same amount would be critical. And now the safe amount would be reduced to about 300 grams or about 10 ounces. That's a piece about this size.
No wonder you have to be so careful.
Shall we go on to the next stage of fabrication, Norman?
Yes, but before we do that, let's review the steps we've seen. You remember, we saw how the technicians get the plutonium into the glove boxes using the bird cage and the plastic pouch. Then we saw the plutonium being weighed, after which some other stabilizing metals with rather fanciful names were added. Finally, we saw the addition of some uranium. Now we'll pick up the procedure from that point.
In this glove box, they have cast the plutonium alloy. First, all of the constituents, the plutonium, the metals, which simulate the fission elements produced in the reactor that can't be removed, and the uranium, are melted together in this crucible. This gives us a homogeneous alloy with uniform properties. Then the metal is melted again in our injection casting furnace. The pins are cast in inverted glass molds. These molds are being installed in the furnace now. This furnace is quite unlike any casting furnace you may have seen. We don't pour the plutonium into the molds. We suck it up into these glass tubes. To do this, we lower the tubes, like these, into the molten plutonium. We create a vacuum within the tubes, and the metal is drawn up. This is all done in a tightly sealed pressure chamber. After the furnace is cooled, we remove the mold tubes and break the glass away. The process takes a couple of hours.
After an exacting process, the fuel pins have been cast, each one 1/8 of an inch in diameter and 19 inches long. What's the next step, Art?
The castings are visually inspected and weighed as a group. They have been x-rayed, and now the technician will compare the actual pins with the x-ray photograph of the same pins to see if there are any small flaws in them. Then they're transferred to the machining lines. Here the machinist will cut them to the length of about 14 inches. The castings are within 1/1000th of an inch of the specified diameter when they are removed from the molds.
I noticed that he's opening what looks like a plastic box there. What's that for?
That is a hood to collect the metal that he cuts off. We must account for and weigh every bit of excess metal. The finished fuel pins are carefully measured for length and diameter. This information is used in determining the amount of sodium that will go into each rod. We must also keep careful track of these measurements as well as those of weight and density, so that we can determine exactly what happens to each pin when it's irradiated. We must measure it before and after irradiation. The information is particularly important because we've been making experimental fuel rods. We must learn exactly what happens to them in the reactor. The fuel is also analyzed chemically and then subjected to many physical tests. When we have finished here, they will take the rods to another glove box for loading into the niobium jackets. A radioactively clean glove box is used to reduce the risk of contaminating the outside surfaces of the jackets with radioactive dust. This man is using a sodium extruder. The machine forces out a small sodium wire. A carefully measured piece of this wire will be placed on one of the jackets for the fuel specimens. The jacket is sunk in a hole in the floor of the glove box to make it easier for a man to do his work. You'll notice he is using a cylindrical fitting with a small funnel-shaped opening. This keeps the sodium off the lip of the jacket, and it is necessary because very small traces of sodium cause defective welds. We want to cover the fuel pin with molten sodium to a depth of about 5/8 of an inch. Next, the fuel pin is carefully loaded into the jacket, and a plug is placed in the top. He discards the funnel, and this is the small closure plug. The whole rod will then be placed in a small vertical oven. You see the oven here. The sodium will slowly melt and fill the space around the pin. Finally, the plug will be welded into place to form the final closure of the fuel rod.
I assume the weld is made to seal the jacket so it can't leak.
That's right. They are using a miniature arc welding process. You can see the arc weld now. After welding, the weld is inspected. Then it's transferred to a clean hood where it will be surveyed for radioactive contamination. The entire rod is tested with a sensitive radiation detector to make sure that there's not the slightest trace of contaminating dust. If they're clean, they can be removed from the glove box. The rods are sealed in a compartmented plastic pouch. 3 parallel seals are made. The middle seal can be cut with a pair of scissors. The top seal prevents air from entering the glove box, while the lower seal protects the pouch. This allows the pouch to be removed without introducing air into the helium atmosphere. just to make sure that there's no contamination. The edge of the pouch is checked with a counter. With this equipment, we are making some of the final tests. The fuel rod is placed in a tightly sealed chamber that is instrumented to detect any tiny leaks that may still exist in the jacket. Then the fuel rods are tested electrically to detect bubbles in the sodium and to determine the position of the fuel pin and the level of the sodium in the rod.
From what we've seen, this looks like an expensive process.
It is. The plutonium itself is costly. Processing and fabricating, too, are expensive. We're constantly searching for better and cheaper methods of processing and making fuel at this laboratory, as well as at others operated for the Atomic Energy Commission.
Thank you, Art. In our lifetime, many communities will use electricity produced by plutonium-fueled reactors. But more important, our energy supplies of the future will depend on this amazing man-made element. As we've seen, a little plutonium goes a long, long way. In fact, the reserves of uranium that can be converted into plutonium represent from 10 to 50 times more energy than our reserves of coal, oil, and natural gas. Extreme precaution and precision are necessary in making this fuel of the future. We've seen the safeguards that must be taken in the laboratory, the helium-filled glove boxes, the birdcage containers, the airtight alloy tubes, and the exacting standards of weighing, measuring, and testing that must be maintained. 25 years ago, the word plutonium couldn't be found in a dictionary. Tomorrow, through the efforts of research scientists, that word plutonium will be as common as coal and oil are today. Such is the world of science, a constant search today to answer the challenge of tomorrow. Challenge has been produced through a grant from the United States Atomic Energy Commission's Argonne National Laboratory. Argonne is operated by the University of Chicago. This has been a Ross McElroy production for National Educational Television.
This is NET, the National Educational Television Network.